let's get back to what we're doing. So, just a little recap for the next 5 minutes. So, the first thing is that we define intensity of radiation. Okay, so we define intensity, which is going to be a function of the wavelength at which the emission or irradiation occurs, and of course it's going to be a function of the position and temperature. So that's the first definition we had, and then we defined what is the, that's the flux of radiation emitted or received, etc., at a certain wavelength. And note that these flux is defined based on the, if it's an emission, it's defined based on the area of the surface which is emitting, and if it is receiving, it's based on the area of the surface which is receiving radiation. Okay, and then we define the, all these huge integrals, spectral, hemispherical, etc., hemispherical quantities, and that's pi by 2, whatever is that intensity quantity, multiplied by sin theta cos theta d theta d phi, where theta and phi are the angles in the 3-dimensional coordinate system. And then we define total flux because it's a function of the wavelength. So we need to define, so if this is called as, let's say, E lambda, then for emission, then you have E lambda of T, D lambda, that gives you the total flux. Okay, that's E. Okay, and this is only a function of temperature. And then we looked at blackbody radiation, and we looked at some of these laws for Stephen. We saw Planck's law. So Planck's law, and in fact Planck's law is the constitutive relationship similar to what we saw as Fick's law or Fourier's law in heat transport and Fick's law in mass transfer. Planck's law is the fundamental law which describes radiation, and from that we found the Stephen-Wiens displacement law, and we also found Stephen-Boltzmann law / constant, okay, for describing radiation properties. That's what we found. Yes. Okay, so the question is, what happens when you integrate from 0 to pi? If it's a surface emission, you can't do that to start with. Now, if it's a volumetric emission, that's a different story. We will deal with it later. In volumetric emission, that is correct, you will have to integrate it everywhere, and we will see, because there you have absorption and you also have transmission. So that will take care of it in being non-zero. So in this case, if it is a surface emission, you cannot integrate it with 0 to pi. It has to be 0 to pi by 2 on the angle theta. Okay? Because it's a surface emission, you cannot see the other surface. You cannot see the other side of the surface. It's only seeing the top side. So you have to integrate only in the upper hemisphere. Any other question? Alright, so we are going to, and we also looked at definition of emissivity. So that's where we stopped in the last lecture. So we're going to take it forward from here today. So we initiated discussion in the last lecture for definitions of absorptivity. Okay, so that's where we're going to start. As observed in the last lecture, the purpose of such definitions is that in a real surface, so note that black body is considered as a standard. So if you want to describe the radiation emission from real surfaces, it comes very handy if you know these parameters, these intrinsic properties such as emissivity and absorptivity. So note that emissivity is described based on the corresponding black body radiation, while absorptivity is defined based on the total incident radiation. We are going to see in today's lecture how to characterize it for a real surface. So far we never in radiation, the last two lectures, we never looked at the actual real surface, and today we are going to see how to actually characterize some of the real surface properties. Alright, so alpha is the symbol which is given for absorptivity, which is in line with the nomenclature given in your textbook. That's going to be a function of the wavelength, and that's going to be a function of the position as well. That's defined as the ratio of the intensity of radiation that is absorbed, which is a function of position and the wavelength, divided by the total incident radiation that is received by that surface. Okay. Now supposing I draw a surface here, okay, there is a certain amount of radiation that is received by the surface, okay, that is an incident radiation. So there are three possible ways in which the radiation can be split. Okay. One is it could be reflected, some amount of radiation can in principle be reflected, and if it is a finite surface of, let us say, thickness L, then some of it could be transmitted. Okay. If I say tau for transmission, and some of it could in principle be absorbed, right. So whatever incident radiation that comes into a surface can actually be absorbed or reflected or transmitted. So if the incident, if we know what is the total incident radiation, then the absorptivity is simply defined as a local absorptivity is simply defined as the ratio of the amount of radiation or intensity of radiation that is absorbed divided by the total incident radiation. So once again we can define things like spectral, hemispherical, etc., because it is positional dependent and wavelength dependent. So we can define quantities called the spectral hemispherical absorptivity. So this is spectral hemispherical absorptivity, and that's defined as, what will be the definition? Based on what we have seen in the last lecture and before, it will be the ratio of, right. So it's the spectral hemispherical, so that's given by G lambda absorb, that's the spectral hemispherical irradiation that is absorbed by the surface divided by the spectral hemispherical that is incident to that surface. Okay. But we know from definition, right, of the spectral hemispherical quantities, this is 0 to 2 pi by 2 so sin theta d phi divided by d phi. Okay. But from the definition of absorptivity, we can replace the incident absorptivity in terms of the incident intensity of absorption with the absorptivity, which is an intrinsic property of that system. Okay. So that we can rewrite as so we can simply replace this as alpha I lambda I into alpha lambda theta. Okay. So that's absorptivity multiplied by the incident irradiation. Okay. So supposing if the incident irradiation, okay, if this is a diffuse irradiation, okay, it means that the irradiation that is received by the surface is the same in all directions in the hemispherical coordinates. Okay. At every direction in the hemisphere, the incident irradiation is the same. So in which case, what will this be? What will be alpha lambda? 1 by pi. Okay, so it will be 1 by pi. So I lambda I will come out because it is independent of theta and phi. So that will cancel out, and the integral of the sin theta cos theta d theta d phi is nothing but solid angle of a hemisphere. So that will be 1 by pi integral 0 to 2 pi alpha d theta d phi. Okay. Similarly, one could define what's called the total absorptivity. Total absorptivity, and that will be alpha, which is only a function of temperature. Once again, by definition, it will be integral g lambda divided by integral 0 to infinity absorbed. Okay. So that's the definition. So once you, I'm sure most of you would have practiced how to write these integrals and understand what these integrals are. So you have to practice a lot more to get a feel of how to write these spectral hemispherical quantities, because any time you deal with any radiation problem, you're going to see this all over the place. And in fact, maybe after this lecture, I'll probably not even write these spectral hemispherical integrals. When I say it's subscript lambda, it's understood that it's spectral hemispherical. If I write simply alpha without a subscript, it will be total quantity. So you must understand what these integrals are as quickly as possible, otherwise it will be very difficult to follow what's happening in the class. Okay. So we said that in a surface there can also be reflection and there can also be transmission, right? So one could, in principle, similar to absorptivity, one could define quantities called reflectivity and transmittivity. So I am not going to write all these gory integrals again. So reflectivity, which is defined as, which is the symbol that's used is rho. So lambda comma theta means it's the local reflectivity. Rho of lambda is the spectral hemispherical reflectivity, which is only a function of lambda and temperature, and rho of t is the total reflectivity, which is only a function of temperature. Okay. Similarly, one could define what's called the transmittivity. Tau is the symbol that's used for transmittivity. Once again, you can define local transmittivity. It's only a function of lambda, which is the spectral hemispherical transmittivity, and total, which is only a function of temperature. Okay. So what is alpha plus rho plus tau? Total absorptivity plus total reflectivity plus total transmittivity. Yeah. It's 1 because all the ratios are defined based on the incident intensity. So the only 3 possible ways by which the irradiation can be split is these 3 modes, and therefore this should be equal to 1. And similarly, that's also equal to 1, right. It's very straightforward to see this. Any questions so far? Alright, so we are going to move to the next topic, which is Kirchoff's law. Okay. So just like how we wrote energy balance when we discussed conduction, so Kirchoff's law is actually the first step towards quantifying radiation in any real surface. So we had looked at blackbody radiation. In fact, we are going to start by looking at blackbody radiation. Kirchoff's law actually relates to blackbody radiation, but eventually what you will see, what comes out of this law is essentially some quantifying aspects of the real surface. So note that real surface, blackbody is an idealization, and there is no surface which can emit more than blackbody, right. So it's important to come up with characterizing principles of blackbody, and that will help us to understand or quantify the radiation from a real surface, simply because we have defined emissivity, which is actually ratio of the emission from a surface with respect to the blackbody. So if we know blackbody, we are done, right. So what Kirchoff's law would do is, supposing you assume that there is a large enclosure, that's a large enclosure, and let's assume that it's adiabatic. There is no heat that is being lost, and let us also assume that there is somehow some heating is done to this large surface, okay, such that the internal temperature is maintained constant. Okay, so internal temperature is isothermal. So it's a large enclosure, and the internal surface temperature is maintained constant. Okay, and let's assume that it's vacuum conditions inside. We haven't dealt with what happens if it is non-vacuum. We will see that towards the end of this radiation section, how to incorporate the effects of media. Okay. So let us assume that there are, let's say, n objects which are suspended. Okay, there are n objects which are suspended inside this large enclosure. Okay, and the surface area of each of these is A1. Okay, so that's the surface area. So A1, A2, these are the surface area of the objects. And supposing if the surface area of the large enclosure is As, and let us assume that Ai for all I going from 1 to n is much smaller than As. Okay, it's just a mathematical notation for all. Okay, so let us assume that the surface area of all the n objects which are suspended inside this enclosure is significantly smaller. So these are all minuscule particles which are actually floating inside this large enclosure. Okay, and let's say that the temperatures are T1, T2, etc. up to Tn. So that's the temperature of the surface. Okay, is that clear to everyone? Supposing if you wait for a long time, okay, wait for a long time and the system has achieved a certain equilibrium. The exterior is adiabatic. Supposing I say that there is a wall here, and I know how to heat it, I put an electrical wire inside and heat it. I can maintain a constant temperature inside. Why is that a problem? I can always do that. So let's say, so the purpose of saying adiabatic is that there is no heat loss from the surface to outside, that's all. It's a complete system. So let's say at a long time, if the system achieves an equilibrium, what will be the temperatures of the small objects inside? What will be the temperature? It will be Ts, right? Because the only temperature which can be maintained is Ts, and so T1, T2, T3, etc. that will be equal to the temperature of the surface at equilibrium. Okay. Now, what will be the nature of the inside surface of the large enclosure? Or let's say nature of emission, let's say. Nature of the inside surface, or let's say nature of emission from the inside surface. What will it be? At equilibrium. Yeah? Only? Yeah. So let's assume that there's only radiation process. Let's not worry about conduction right now. Blackbody is a diffuse emitter. It absorbs everything. What's the object which is closest to a blackbody approximation? So you have a large enclosure with a small pinhole somewhere, and that body behaves like a blackbody because there is a significant internal reflection of radiation, and so everything which comes in is actually kept inside. So what you see here, this surface is very similar to the approximation that we made for a blackbody. So whatever emission that comes from, so because the surface area of all the objects that we have considered is significantly smaller than the surface area of the enclosure, there will be significant total internal reflection inside the enclosure, and therefore the inside surface of this enclosure is going to behave like a blackbody. Okay. That's a fair assumption to make. So it's going to behave like a blackbody, and therefore the emission that comes out of that surface is it's a blackbody radiation, right? So the answer is and that is, so the total blackbody radiation is going to be EB, which is only a function of temperature. Okay. So note that I have already skipped the integrals, gory integrals. So when I don't put lambda here and angular dependence, it means it's a total quantity. There's no need for a pinhole because these objects, they behave like that. So these are real surfaces. So there's emission that's going to occur from these objects. So note that in the blackbody approximation, we said there is a pinhole and some radiation comes through the pinhole and it gets totally reflected inside. And these objects exactly do the same. In a blackbody approximation, the emission from that hole is only to the surroundings. It doesn't mean that there is no emission inside. Whatever is emitted inside is also absorbed. So there is emission in every location on the surface. It is just absorbed in all other locations as well. That's what you mean by total internal reflection, right? So in the same way here, whatever little is emitted, only very small quantity is actually intersected by these objects. It's very similar to the pinhole example that we had before.